We can also use the central limit theorem to approximate other distributions, specific ones. Now, on the sheet here, you see examples of 4 different binomial distributions. Now, I've kept the probability of success constant, but just increased the value of n. So what you should see is that for very small values of n, so in the first instance when n is 4 or when n is 10, the shape of them is skewed. But even as early as 10, you can start to see that the shape is changing. As the value of n increases, you're starting to see that it starts to look more and more normal, more and more symmetric. Now, this is no accident. It's all due to the central limit theorem. When we've got a binomial variable here, when we talk about x, remember that x represents the number of successes that we have in n independent trials. So more precisely, x is a total of all of the outcomes from each trial, x1 plus x2 all the way down. Now, from chapter 3, we remember that the expected value of a binomial variable is np, and its variance is np1 minus p. Now, the key here, the connection to the central limit theorem, is that this x is once again the average multiplied by n. So by the central limit theorem, I know that this is going to be given, or this gives me, x bar is normally distributed, and in this each individual case, each xi has the following. For a single trial, we know that the probability, the mean outcome, is 1 trial times p, so p is the expected value for a single trial, whereas the variance of a single trial is 1 times p times 1 minus p, which is p into 1 minus p. So according to the central limit theorem here, we are going to get that this is p into 1 minus p, that's the variance, but remember we're dividing by n. So the central limit theorem tells us that the average has to behave this way. Now, just like we did in the previous examples, by the properties, we know that nx will also be normally distributed, right? A scaling of a normal random variable is still normal, but by the properties we've talked about, this n will scale the mean by n, and that gets us the np like we expect, and we'll get an n squared into p 1 minus p over n, and just like we expect, this binomial variable, the one that we've got there initially, can be approximated by a normal distribution that looks exactly like this. And so it is no accident that the pictures above start to look more and more normal as n gets bigger. When n gets bigger, the central limit theorem kicks in, and it turns this total into a normal distribution, and the center of the normal distribution is just the mean of a binomial, and the spread of this normal distribution is related to the variance of this binomial. Other example to do with car insurance. And so we'll say that x is the number of uninsured drivers in a random sample of 50. So let's say that x is the number total of uninsured drivers. So that means x is going to be x1 plus all the way down to x50. N will be 50. P will be 0.25. Success in this particular example means uninsured. Okay. Now, we know this is a binomial distribution. If we've got a random sample of people, we're going to assume that they're all independent. We know that X should follow a normal distribution, where this is 50 for n, 0.25. And so the probability of getting less than or equal to 10, we could just use R, and this would be a p binomial problem, where we've got 10, we've got 50, and we've got 0.25. So those are the right parameters that we need for the binomial distribution. Now, if you just go ahead and calculate that, you'll get 0.2622. Now, if we would like to use a normal approximation, and we're going to use the central limit theorem, it is approximately true that X here is going to be normally distributed NP into 1 minus p. And in this particular case, that would mean we'd have a normal distribution of 12.5 as our mean, and we would get 12.5 times 0.75. We can easily plug in that value as we need. And that's going to end up giving us a normal distribution of 12.5 and 9.375. If we were to plug in and use the central limit theorem, then all we need to do is just do a simple p-norm calculation. We'd get 10, 12.5, and then the square root of 9.375, right? If we just used R to perform this calculation, these are the values we'd get. And R spits out this value, 0.2071. Now, I don't think this is that good. Why is this approximation, not very good? But there's an issue in using the central limit theorem to approximate discrete random variables. The graph of a discrete random variable has bars, and that means they've kind of got a finite width. The central limit theorem tells us that we have a normal distribution, and this is a continuous random variable. If we want to use that to approximate a discrete random variable, then when we overlay the two, this is the kind of thing that's going to happen. When we do a discrete random variable, we've got a bar that's a half a unit in width each way. So when we put a normal curve and we want it to go through this discrete approximation, if it goes through and we talk about the location of 10, and we talk about saying the probability that X is less than or equal to 10, if we stop it directly at 10, we are only taking half of this bar. So it only uses half of the X equals 10 bar. So we're missing half the bar. And so what math people kind of figured out is they said, well, we don't really want to miss half the bar, because in the discrete case, that X equals 10 fills up technically that whole bar. So they introduce what's called a continuity correction. And the continuity correction is basically saying add in the missing part of the bar when you use the normal approximation. And so what do I mean by that? Okay, So if we were to talk about these situations like we've got here, again, here is our bar at 10, and we've got our normal curve kind of going through. This is the part that's included. So if we were asked the question, probability x less than or equal to 10, or probability strictly less than 10, this is the part that we need to include. So we have to include this, and that means we are going to move the value of 10 over a half step. We're going to move over 0.5 units. So the correction says that if you want to get a better or more accurate answer, slide the bar over so that you include, slide the curve over so that you include the rest of the bar. And in this particular case, that means slide the bar over so that you include that whole thing. And that means take your calculation centered at 10.5. Now, if you were asked the other way, so let's say that we were asked p x greater than or equal to 10 or p of x greater than 10, we've got our curve and it kind of goes through a certain spot, right? We need to slide things over. And so if we were drawing our curve and we wanted to say x greater than or equal to 10, so if this is location 10, if we are going x greater than 10, this is what we are currently taking. But we have to include this portion. We have to include the rest of the bar. And that means we are going to slide over another 0.5 units to include the full bar. So that means that continuity correction would say, if you really want this type of thing, you should slide the bar over to 9.5. So slide the bar over to 9.5 to get a more accurate result. And when we return back to our problem from above, we were asked to calculate the probability that x is less than or equal to 10. So we are going to include the continuity correction. That means the question that we should really be calculating is, what's the probability that x is less than or equal to 9.5? Because as I said a moment ago, we want to include the rest of the bar, right? If we are asked to go this way, we need to include the rest of the bar. Oh, sorry, my mistake. We should be going to 10.5. I apologize. Now, if you do that, and you go ahead and you use p-norm, and let's say we go p-norm 10.5, the 12.5, and square root of 9.375, if we go ahead and use r to calculate that value, we'll get 0.2568, which is much better than we had before. So the central limit theorem is the underlying mathematical fact that allows us to replace a discrete distribution like binomial with a normal. But if we actually want to put it in practice, we have to involve what's called this continuity correction. Because because taking values like 10, we typically miss half of a bar. That means we need to slide things over to include the rest of a bar.